In this lecture, we continue our discussion about arrays. In this lecture in particular, we want to discuss how we solve systems of linear algebra under this module. We also discuss calculating eigenvalues and eigenvectors. To solve a systems of equation like a times x equal to b that is given in a matrix form, we can use the linear algebra package linalg of numerical Python. So consider that we have 5 equations and 5 variables. Then we are able to solve this systems of equation. So first, in the A matrix, we have a coefficient matrix and B is a right-hand side vector. So as you can see in this example, we first import numerical Python dot linear algebra. So linear algebra is defined under numerical Python. Then I assign a nickname named LA. It's a short version using the as a statement, and then we import numerical Python and random libraries as well. First, we generate 2 matrices. The first one is a random number between 0 and 1, and the size is 5 by 5, 5 rows, 5 columns. The other one is a vector with 5 rows and 1 column. We apply the dot method, we multiply these 2 matrices, and then that becomes the B vector. If we apply solve method under linear algebra, then we can find the variables for the system of equation. So let's try implement this in a notebook so you can see what the results look like. First, we import numerical Python dot linear algebra, and then I call it LA, which is a short version. Then I import the numerical Python as NP, then import the random module. Then we generate 2 matrices, A and P dot random. We use the rand function, which generates a random number between 0 and 1, and the size is 5 by 5. The other matrix, NP dot random dot rand, but size is 5 by 1. Let's run this and let's print to make sure. Okay, we have 5 rows, 5 columns, and for x we have 5 rows and 1 column. Then we multiply these 2 matrices by applying the dot method. So we assign it to b. B is equal to np dot function a and x. We can print. So now it's an array with 1 column. If we apply shape, then we know its size, which is 5 by 1. So that becomes the B, the right hand side of the systems of equation. And if we want to solve that system such that A is the coefficient matrix and B is the right hand side, then we first call linear algebra dot solve method. So we expect to see 5 values because we have 5 equations and 5 variables. So 1, 2, 3, 4, 5, and that's how we solve systems of equation. Now, here is the practice. This one makes better sense because we see the equations and the variables. So solve the following systems of equations. It means that first we need to define the coefficient matrix. For example, for the first equation is 1, 1 minus 2, 1 plus 3, and minus 1. And the right-hand side or B matrix are 4, 20, minus 15, minus 3, 16, and minus 27. So let's quickly solve these systems of equations. So to define the matrix, we apply the array method, and then we define lists of lists. So each row is saved in one list. The first row is 1, 1, minus 2, 1, 3, minus 1. The second list or row is 2, minus 1, 1, 2, 1, minus 3. The third row is 1, 3, minus 3, minus 1, 2, and 1. Next row is 5, 2, minus 1, minus 1, 2, and 1. Next row is minus 3, minus 1, 2, 3, 1, 3. And the last row is 4, 3, 1, minus 6, minus 3, minus 2. Okay, let's run this. Then let's take a look at the coefficient matrix. 2, 3, 4, 5, 6. 6 rows and 6 columns. And now the B matrix, which is np dot array. Then I use list of lists. The first list is 4, 20, because we want to have 6 rows. So 4, 20, minus 15, the right hand side of the third equation, minus 3, 16, and minus 27. Let's run this and look at the B matrix. Okay. And now we can apply the solve method. X, I can change it to y equal to LA. We call the linear algebra. And then solve. We pass A and B. So we expect to see 6 values, 2, 3, 4, 5, 6, because we had 6 equations and 6 variables. So that's how we can simply solve systems of equation using the linear algebra functions. In this table, you can see commonly used linear algebra functions. For example, with diagonal, it returns the diagonal elements of a square matrix as one-dimensional array. Dot, as you have seen before, it returns it actually calculates the matrix multiplication. Trace, compute the sum of the diagonal elements. DET, compute the matrix determinant. And in inverse, compute the inverse of a square matrix. EIG, which compute the eigenvalues and eigenvectors, and we are going to discuss this more in this lecture. Eigenvalues and eigenvectors are useful techniques in analyzing high-dimensional data. Finding eigenvalues and eigenvectors is important in linear algebra because they allow us to reduce a linear operation to separate simpler problems. For example, diagonalization of a matrix with distinct eigenvalues. Diagonalization means transforming a non-diagonal matrix into an equivalent matrix, which is diagonal, and therefore it's simpler to deal with. Here we can see a few applications. For instance, we can model population growth using an age transition matrix and age distribution vector, or natural frequency of the bridge is the eigenvalue of the smallest magnitude of a system that models the bridge. There are other applications such as facial recognition algorithms and etc. Let's take a look at the concept of eigenvalues and eigenvectors before we run them in a Python notebook. Let's say A is an n by n matrix. Now the question is, are there non-zero vectors, such as x, that ax is a scalar multiple of x? So here, in this graph, we have x-axis, y-axis, and then you see vector x. Lambda dot x is equal to a times x. So lambda is a scalar multiplier, and x would be the eigenvector. So technically, A, our n by n matrix, times the eigenvector equates to eigenvalues times eigenvectors. And you can see that here, once we have the x vector, lambda, which is a scalar, dot x, is easier to deal with. So here's the numerical example. Let's say A is a 2 by 2 matrix, and x1 is this vector. Now we want to see if x1 can be the eigenvector for this matrix. So to test this, we multiply A and x1. So we have two matrices, we multiply them, and the result is a 2 by 1 matrix, 2 rows, 1 column. If you take off 2, then 2 times 1, 0 would be equal to 2 times x1. So 2 is the eigenvalue, and x1 can be eigenvector. In Python, we can compute the eigenvectors and values of different matrices. In this example, let's say we want to generate a unity or identity matrix with all elements are 0, but the diagonal elements are 1. And there is a function named EIG under linear algebra which returns both eigenvalues and eigenvectors. So first we generate a unity matrix. The size is 3 by 3, and then we apply or calculate the eigenvalues. In the other example, first we generate a random matrix 3 by 3, and then numbers are randomly generated between 0 and 1 because we are applying the rand function. And then we calculate eigenvalues and vector with calling EIG method. Let's try to implement this and see what the results look like. The first matrix A is equal to mp dot I. So I is the new method that we are learning in this lecture. Last time we talked about zeros. We generated a matrix with 0 values. This one generates a unity matrix or identity matrix. Let's print this so you can see the diagonal elements are 1 and other elements are 0. Now to calculate the eigenvalues and eigenvectors, I define two variables. Then we call the linear algebra dot eigenvalue, and we pass A to that function. So to see the result, we print eigenvalues, and to see the eigenvectors, we print eigenvectors, and you can see, because this is a unity matrix, we have 3 eigenvalues, and the eigenvectors are again a unity matrix. Now in the second example, we generate another matrix with rand function np.random.rand, and the size is 3 rows, 3 columns. Then we calculate the eigenvalue and eigenvectors with one line of code called linear algebra eigenvalue of A. Now if we print the eigenvalues, we can see there are 3, it's an array with 3 elements, and the eigenvectors is a 3 by 3 matrix. Now one common question that I usually get, do we have to define variables, e-values or e-vectors? No, these are arbitrary. Let's change them to A and B. If you run it and then you print A, you see the same, you get the same result, or B for eigenvectors. So the first one is eigenvalues, the second one is eigenvector, but you can assign different variables because we can define different variables. And with that, I finish this lecture.